All right, here we are. We're going to talk about Module 11, ocean currents. And ocean currents are huge for us. They really are a big driver of our whole Earth climate. And so we're going to talk about how they're driven by temperature and gravity. They're going to be driven by prevailing winds and the Coriolis effect, as well as salinity. And, of course, the continents get in the way of these ocean currents as well. So don't worry. We'll see this image again. Gravity. So gravity does move the ocean. So warm water, it expands just like air does. And down at the equator, it's warm. This is a map of surface temperature anomalies. And you can see that there is some warmth off the equator here. And there's warmth off the equator there. And there's also some southern hemisphere heating here. This is probably fall for us or winter. And then up here, you're a little colder. You have some spots. So you see the surface temperature anomalies. But check it out. The equator, when the water gets warm, is 3 inches taller than the mid-latitudes. Mid-latitudes would be more like where we are. And so, of course, gravity pulls water away from the equator. Because it's up higher. That's a whole potential energy stuff. So you get that pulling away from the equator, and you end up getting this thing called gyres. Gyres are large-scale patterns of water circulation. The ocean surface currents rotate clockwise in the north and counterclockwise in the south. And I'm going to show you the same thing on the next screen. But you'll see that clockwise rotation here and that counterclockwise rotation here. So let's look at it closer. So let's look here in the Atlantic. So I mentioned already in the year how these ocean currents and these wind currents drove trades during colonial times. So, they come off of England, hit themselves up here in Africa and do some work, and then they come across the Caribbean in the colonies again. Well, these things are all over the place in the other oceans as well. But they're driven by this equatorial, the pushing. See, it's warmer here, and so the ocean pushes it all away here and away here. Same down here, pushes it away. So you see this word called upwelling zones. That's what's next. Upwelling zones are places where the surface waters diverge. And because the surface waters are moving away from that point on the map, cold water from below rises and it brings up nutrients from the ocean floor. So this is awesome if you're a fish because this feeds the producers and supports large marine ecosystems. Upwelling zones, let's look at these again. Upwelling zones are some of the most productive fisheries on the planet because of this upwelling. It brings up all the dead stuff that has settled on the ocean floor. It brings it up and feeds the fish. Well, it feeds the algae, which feeds the fish and all that. Another really big important thing is the thermohaline circulation. Thermo meaning heat, haline meaning salt. So it's driven by heat and salt. Oceanic circulation pattern that drives the mixing of surface water and deep water. So your water evaporates and it freezes. It gets colder and dense and it sinks. And it circulates along the ocean bottom. And it rises in certain places in the equator. And it gets warm again. And it does the same thing. Let's see this image bigger. So let's say you start off here, off the Gulf Coast. So warm water flows from the Gulf of Mexico to the North Atlantic where it freezes and evaporates up in here. The remaining water is now saltier and it sinks to the bottom of the ocean and it circulates along and some of it's going to diverge and come up here in the Indian Ocean and some of it's going to keep going around the Pacific and then come up here off of Alaska. It's saltier and it sinks. The cold water goes along and then it comes up in certain places. Now you've got a shallow warm water current that comes off of here and helps drive, again, our trade follows those currents. Okay, but not only does it drive trade, but it drives climate. So check it out. Here's where we live. If you draw a line across the map, we're equal with Spain or so. You don't think of Spain as having the same climate as we do. Let's look at this one, though. What about England, and Newfoundland. Because of this thermohaline circulation, this warm water that's really heated up off the Americas cuts across the Atlantic Ocean and runs into the United Kingdom. And because of this, because of Europe in general here, really gets hit by this moderate temperature coming across. So it's very, moderate's the right answer. Because of this, England's winter is 20 degrees warmer than Newfoundland. It keeps England very mild. So I wanted to see, okay, let's make a comparison. Climate of London. Cool winters and warm summers with frequent precipitation. And they only get snow. So let's think about winter. They only get snow on average 16 days a year. And usually it's not a lot of snow. And it melts off very quickly. So that's London. But what about Newfoundland? St. John's, Newfoundland. It's right off the ocean. A very different climate altogether. And where's it at? 30 inches in a day. 3 meters of snow. 132 inches a year. That's really different than London, straight across the ocean. And that's just what I want you to compare when you look at this, is that heat is being delivered to keep England and Europe, for that matter, a lot more moderate in temperature than a similar latitude across the globe. Then there's El Nino. So El Nino is a huge climactic driver. In a normal year, the Pacific trade winds flow from east to west, and the surface waters flow from east to west. They well up off of South America, and they cut across the ocean over towards, Indonesia and Australia and all that. In an El Nino year, you get an increased surface temperature off the western Pacific. And I know in my mind, I had to wrestle with the idea that we are the western Pacific. We're on the west side. Okay, America is the west side of the Pacific. Over here is America. We're on the west side. So there's a warming of the western Pacific. And what happens is the trade winds in an El Nino year flip-flop. Instead of east to west, they go west to east. And you don't get the upwelling. And it drives climate for, the new world. The whole climate gets shifted because of this. It's a very dramatic thing. And so I was thinking about, all right, what can I tell you guys that would help you understand how El Nino affects us? And so I did a little looking, and based on data collected, they did a study here. Based on data collected, El Nino will affect the climate of the Ohio Valley and the lower Great Lakes. Weak El Ninos cause the climate to be, a little colder than normal. However, during strong to moderate El Nino southern oscillation, that's what this means, events is high in the Ohio Valley, southern Great Lakes. During a moderate one, the winters in the Ohio Valley are likely to be warmer and drier than normal. This results in below normal snowfall across the region. So I said, okay, so those are normal El Ninos, strong El Ninos do these things. What year do I remember that I can talk about this? And I thought about when I was your age, and here it was. The 1997-98 El Nino event is regarded as one of the most powerful El Ninos in recorded history. A air temperature difference of 1.5 degrees Celsius compared to a normal difference of 1/4 of a degree. What I remember from this El Nino event is growing up on the tree farm. Of course, you're selling Christmas trees in December, and it was the first weekend of December, and it was 70 degrees outside, and I was selling Christmas trees, and I saw a snake. You don't see snakes while you're selling Christmas trees. That's just not normal. And when you look at, this is a temperature anomaly on December 27th. And you just think about, what does this even mean? So you're off of South America right here. And this orange, 2.5 degrees. A difference of only 2.5 degrees was driving this El Nino. This map, look at the dramatic difference in the white areas indicating a pool of warm water. So you got this warm water and this is cooler water, so it's definitely driving the heat back across the Pacific the opposite direction compared to normal. And it really affects just the entire circulation. So then the next thing we're going to talk about are hurricanes. So hurricanes, of course, you get your great big cyclone, very powerful. And this here was a Hurricane Matthew, I looked up. It was a pretty devastating hurricane because it just stayed right off the shore and just bombarded the eastern seaboard all the way up because it just sat there in the ocean and just sucked up energy and just dumped as it went up the seaboard. It was very destructive. You'll notice when you look at this image that, here, let me drag it over here. Hurricane history. So this is since the 1940s, they've tracked, since the 1850s, they've tracked hurricanes. And these hurricanes start here off of Africa and they come up and they hit America and they swoop. You know, some of them, yeah, they drift out to sea, no big deal, no harm. But a lot of them, they come right up, hit all our big fun islands and smack into Florida. Some of them come up the Gulf Coast, some of them hit the eastern seaboard. And some of them will cross and go into the Pacific. Okay. So hurricanes are bad. So another thing to visualize is this was Hurricane Matthew again, and they superimposed it over Ohio. Just so you could see how big hurricanes truly are. 392 miles, 400 miles across. You know, bigger than our state. These storms are. That's a storm. Just think about all the water that can be dumped out of a storm like this. And again, what goes on with hurricanes, they come up and a lot of them do this curve move depending on where they come aboard. And, the mountain ranges do help drive them. The Appalachian Mountains running up here do drive some of these storms. If they hit, southern enough, they really skirt the bottom of the Appalachian and then they come up at us and we get dumped from them. But a lot of them stay to the east of the Appalachians and we don't get them so bad. And that really does represent the end of this section.